And let's talk about maps today. Maps are a little bit different, so especially I think for this group of students, because you don't normally see these in an introductory C course. I'm not sure if they would have told you about these in your data structures course. So these go by different names depending on the programming language or depending on whether you're taking these in a data structures course. In a data structures course, they're probably called associative arrays. Python, they're called dictionaries. In Java, they call them maps. They're all names for the same abstract data type. Right? So a data type is just a type, right? So we've been talking about types already. An abstract data type, they might have told you about this in your data structures course. An abstract data type is actually a formal specification of a type. So formal, I mean mathematical. So people who study data types describe these things using mathematics. So you can formally specify types like lists and sets. You can also formally specify this thing called an associative array. You guys won't take Sys 235. You've already taken your the CMPE version of the data structures course. If you were to take Sys 235, though, you would learn how to implement how an associative array or map or dictionary is implemented. Now, a map you can think of as being a list, right? Now, remember, in a list, you use an integer index to get or set or remove an element in the list. A map is kind of like that, except the index is not can be an integer, but it can be anything else. Right? So you can use any reference type as your index, right? Which means you can map a string to another string, right? Or you can map a double to a string, or you can map a string to a double, or things like that. So you can use any reference type to get to the element to get to the element to what we call the key maps to. Right, so I'll explain what a key and an element, or a key and a value are shortly. Like sets and lists in Java, you get your choice of what type of map you want to use. Right. So so that shouldn't be here. So a hash map is like a hash set. Right. So very fast, but you can't tell what order the elements are stored in. A tree map is like a tree set. So not as fast as a hash map, but you know that the keys or the indexes, those are sorted. The third kind is also occasionally useful. So you have something called a linked hash map. It's like a hash map, so it's very fast, but the indexes are stored in the order in which you put things into the map. Okay, so a map models a group of elements that are accessed by what are called the keys. So the keys are just your indexes. All right, that's all they are. So in a list, your indexes are 0, 1, 2, 3, 4, up to the size of the list -1. Right. So in a list, the indexes are unique. Right. There's the index 0 maps to in a list. The index 0 maps to exactly one element. Right. The index 1 maps to the second element. The index 2 maps to the third element, and so on. So in a map, the keys must also be unique, right? Because the keys are going to be your indexes. Now, if the keys are unique, they also form a set, right? And that's exactly how the Java map works, right? So the Java map represents its keys as a set of keys, which is why I had to tell you about sets so that you can use a map. Every key maps to one value, right? Maps to at most one value. But you're allowed to have multiple keys map to the same value, right? So in a list, you can put in the values 0, 0, 0, 0, for example, right? Index 0 of the list gives you back the element whose value is 0. Index 1 gives you back the element whose value is 0. Index 2 gives you back the element whose value is 0, right? So just like in a map, multiple keys can all map to the same value. right? So the values that are stored in the map, those are not a set, right? And so what you have is basically a table where one column is your key and the second column is the value associated with the key. Right? So each row of the table is called a key value pair. I'm going to jump forward one slide. So here's an example of, here's an example of a map. Right? So this is a, I guess this is a graphical depiction of a map. So your keys, they're in our first column. Our values are in our second column. Here I've got a map that maps the month name to a value, right? The number of days in the month. Right. February is ambiguous, right? This could be 28 or 29. For now, we'll just assume it's 28. Right. The month March has 31 days, and so on and so on and so forth. Right. So in this example, the important thing here is that the months are unique. Right. There's only one month named January. There's only one month named December. Right. The values are not unique, or are not necessarily unique. Right. Several months have 31 days, and several months have 30 days. Right? And so a map is just a two-column table. The first column has to be, the elements in the first column have to be unique. So let me get rid of this. All right. Each row is called a key value pair. Right? That's it. So there's lots of examples of when you might want to use a map. You know that you've all taken calculus, so you know that a mathematical function is also called a map. Right? And so that's one way you can think about a Java map, right? As a mathematical function, right? Your key is x, your value is y, right? So you should have been taught in calculus that a function maps a value x to exactly one value y. Right, and so you should have also been told that a circle is not a function. Right? The circle can't be described as a mathematical function y of x, right? Because in a circle, for many values of x, there's two values, right? There's two values of y. So if you wanted to represent a circle, you would not use a map, right? You'd have to do something else. A dictionary, like an English or spoken language dictionary, you can think of it as mapping words to lists of definitions. The number of days per month, you can think of the month being mapped to the number of days, right? You can think of provinces being mapped to capital cities. You can't necessarily invert this relationship. So you can't necessarily say that every capital city maps to a province because capital city names are not necessarily unique in Canada. I think that's true. It may not be true, but there's nothing from stopping the province of Ontario from naming a city in Ontario, Quebec City, for example, right? Although I don't think that happens in general. If you have if you have a book that has an index, right, then you can think of the keys as being the keywords in the index, right, and then the values being the set of pages where you might find information regarding the keyword. If I'm keeping the marks for students in a course, then you might use the key, the student number as a key, right? Student numbers are unique, so they're useful as keys. Student names are not unique. So every once in a while, you'll end up in a course where two students have the exact same first and last name. It's not common, but it does sometimes happen. Which is one of the reasons why the university uses student numbers, because the university can guarantee that a student number is only ever mapped to one particular student. So if I'm storing your marks, I can use your student number to map to a list of marks. If I want it to be a little fancier, I can take your student number and I can map that to another map. Right? So that other map maps the name of an assignment to a mark for that assignment. Right? So for example, I can have the assignment A1 mapped to your mark for assignment 1, the name assignment A2 mapped to your mark for assignment 2, and so on and so forth. Right, so you can have a map whose values are other maps, right, or lists or sets. Right, so you can store anything for the value. Right. Similarly, if you wanted to, you could have a map whose key is also a map, but I can't think of a good example where you would do that. Okay, hash map, very fast. It's like hash set, so it's very fast. Gets, put, and contains key. Right. So you can get a value out of a map using get. You can put a value into the map using put, and you can ask a map, does it contain a key, using contain. So we'll look at examples of these shortly. Right, these are all O1 expected complexity. Right, so very fast. Now the hash map, its keys are stored in a hash set. So you know that if you iterate over the set, over the keys, the order that you iterate over, the order is not guaranteed by the map. Right, so your keys could be stored in any order. If you want your keys to be sorted, you use the tree map. And so a tree map uses a tree set to keep its keys, right? So you know that tree set has a fast get, put. Well, sorry, tree set has a fast add, contains, and add and contains, right? So add is analogous to put, contains is analogous to contains key. So you know those have log n complexity in tree set, so you can guess that tree map has those operations have the same complexity. Because the keys are stored in a tree set, you know that the keys are stored in sorted order, right? And that also means that the keys have to be sortable, right? So in other words, the keys have to have a compare to method. Whatever type you use for the key has to have a compare to method. There's also a linked hash map, so that's similar to linked hash set, right? Except in a linked hash map, the keys are stored in insertion order, right? So if you put a key value pair, so if you put a key A into the map, so you put the keys A, then B, then C into the map, then when you iterate over the keys are also A, B, then C, right? So it stores them in insertion order. Okay. So to make a map, there's a key and a value, right? So that's how the map stores things, right? So it stores these key value pairs, right? Which means you have to specify two types when you make the map, right? So my map of capitals, right? That maps a province name to a city name, right? Which means my key type is a string, and my value type is a string. When you use a map, you have to specify the key type and the value type. You don't need to specify them on the right-hand side there, so you can use the empty. The put method puts a key value pair into the map. Right, so I can put value Toronto into the map, and the key that I use to get Toronto out of the map is Ontario. Right, so my keys are the province names, the values are the capital city names. So the province Quebec has the capital city, Quebec City. Province Nova Scotia has the capital Halifax. You're not adding individual elements into the map, right? You're always adding a pair of elements into, a key value pair into the map, right? So you have to specify the key and the value, which is why the method's not called add, right? It's called put, intentionally to force you to use to remember that you have to put both the key and the value into the map. Okay, so here, so that example is this table here, right? Makes this table. If you want to get a value from the map, you have to get the value using a key, right? So this is just like the get method from lists, right? Except in a list, you use an integer index, With a map, you use a key, right? So whatever the key type is, you have to pass in an object of that type, right? So to get the capital city for Ontario, right, you pass in the province name Ontario. And if the key Ontario happens to be in the map, then it will return the value that's associated with Ontario, right? So this will return the city Toronto. If this key is not in the map, get returns null. So you have to be careful about the return value when you use get, right? Because if you get null over here for the city, and then you try to use the variable city to call a method, you'll get a null pointer exception, right? So in other words, when you call the method, it'll fail. So you normally have to check the return value unless you're sure that that key is in the map. So you have to be a little bit careful when you use the return value. Now, if you want to know, does the map contain a key, you use the contains key method, right? So my list of capital cities, or my map of capital cities, it's missing the territories, right? So if we want to put in the territory capitals, we can do so. First, I'm going to check though, right? Does my map, so my map name is capitals, right? Does that map contain the key Nunavut, right? And then I'm going to negate it, right? So in other words, this is asking, is Nunavut not in the map capitals, right? So not. Right? So if it's not in the map capitals, I can put in the capital city for Nunavut, right? Using the put method. Now, is the Northwest Territories, is that not a key of the map capitals, right? So if it's not a key in the map, then I can put in Yellowknife for its capital city, and similarly for the Yukon, right? So is Yukon not, right, not a key in the map? If it's not a key in the map, I can go ahead and put Whitehorse in for the capital city for the Yukon. Right, now, if you use put and the key is already in the map, right? So suppose I make my map and I already put in all the territory capitals, and then I call capitals put Nunavut Iqaluit. Then put will not. What does put do? Does it overwrite? I should look that up. I don't remember what put does. Do I have a web browser handy? I don't have a web browser handy. A second here. Let's see what it does. Okay, drag this over to here. Okay, so what does put do if it's already in the map? If the map previously contained a mapping for the key, the old value is replaced by the specified value. All right, so if Nunavut's already a key in the map, then it's going to replace the current value for Nunavut with this value here. Right, so this is like set for lists. So it will overwrite whatever value is stored, is associated with Nunavut. All right, now where would you want to use a map? So it turns out maps are super useful because it's often the case where you want a list of things, but it's not natural to access the elements of your list using an integer index. Right. So in other words, you really want to access elements by name or something like that. Right. You can imagine if I'm keeping your grades, I really want to get one of your grades using an assignment name. Right. So that's a perfect example of when you'd want to use a map. There's another thing that happens in some types of problems where you want to count the number of times something occurs in a list, for example. Right? So if I have a list of strings, I might want to know how many times every string occurs in the list. Right? You might want to do this because you might want to find the most commonly occurring string. Right? I want to know which string shows up the most, for example. Right? Or, for example, you might want to know what's the least commonly occurring string. So to do that, you can solve this problem using a map. Right? So you make a map. Your keys are going to be the words in the string. Right? So they're the unique words in the string, or sorry, they're the unique words in the list. And then the value is the number of times each word appears in that list. Each string appears in the list. Right. Okay, so I have a list of strings. So T is my list of strings. Count is going to be my map that stores how many times each string appears in the list. Right. So how do I start out with an empty map, right? And then I loop over the list T, right? So for every string in the list T, I'm going to check, is it inside the map? Right. So for each string S, is that string S, is that a key in my map count? Right. So if it is a key, then I know that I've seen that string already. Right. So what I want to do is I want to increase the count of that string by 1. Right. So I've seen the string S again. So now I want to update the map to indicate that I've seen it one more time. Right. Now my map is a map of string to integer. Right. So the integer is the count. The string is the string that I'm calculating the frequency for. Right. So I get the count. Yes. Right. That returns an integer object, right, or a reference to an integer object. I now want to increase the count by 1 and put that value back into the map. It's almost exactly like the dice simulation and the coin flipping simulation, right? Except there we had a list because the index corresponds to the number of times that I saw something, right? Here, the index is now the string, right? The number of times that I see a string. I increase the count by 1 and put it back into the map using the key S. Okay. Now, if I haven't seen, so if S is not a key in the map, right, then I can just put the key S into the map and I can put the value 1 because I've seen that string once now. Right? And so that lets you build a map that counts how many times each string appears in a list. So the keys in a map are unique, which means they form a set. And that means you can ask the map for that set of keys. So there's a method called keyset that returns the set of keys. Right? So count, that's my map from the previous slide. If I want the keyset for that map, you just call the keyset method. Right? And that returns a set of strings, right, which are my keys. This is a little bit different, right? So we haven't seen this type called set yet in the course, right? You've seen hash set, you've seen tree set. I talked about linked hash set, right? But I haven't told you about this thing called set yet. So now is a good time to tell you about set. Where's my web browser? All right. So what is this thing called set? Okay, so set, it's also defined in java.util. Up here, I guess, right? I guess that's the easier place to find out. So it's in the package java.util, and set's not a class. So hash set's a class, tree set's a class. Set's what's called a Java interface. Okay, so it's not a class, but it's still a type. Right? So it's still a type, which means you can use it as a variable type. So an interface in Java is nothing more than just a bunch of methods. Right? So notice there's no constructor, right? There's no fields. It's just a bunch of methods. Right? So if you scroll through the documentation, all you see are methods. In an interface, the methods have no implementation. right? So if you were to go into the source code for the set interface, and you were to look at the add method, all that you would see is Boolean add, that's the element type, and then a semicolon here, right? There's no method body. So in Java, an interface is a set of methods that a class promises to implement. All right, so what does that mean? Okay, so that means if you have something like a tree set, right, then a tree set can say that it implements the set interface, right? And so what that means is that tree set promises to provide an implementation for every method that's in set. Right? So if a class decides to implement the set interface, that class must provide an implementation for add all, clear, and so on and so on and so forth. Right? So what an interface does in Java is it tells you what methods have to be in a class. It specifies what the contract for the method is, right? So in other words, it says what the method has to do, right? But it doesn't say how the method is actually implemented, right? And so that's what lets Java provide a tree set class and a hash set class, right? Where the add method does something, or the add method is implemented in a different way. Right? You people who use hash set and tree set, they all any user knows that the method that the add method exists, and it does this, right? But the tree set and the hash set, they can provide different implementations of the method, so that the method has different characteristics, right? So in other words, hash set can provide a faster implementation of add than tree set, right? Tree set provides a slower implementation of add, but the user knows that the elements of the set are in sorted order. So because now the you know that if you have a tree set, a tree map, then its set is probably a tree set, right? But the map interface, so map is also an interface. The keyset method says that it returns a set, right? So it doesn't say what kind of set is returned, it just says it returns a set. So when you use the keyset method, if you want to store the return value, you have to store it in a plain old set, right? So in other words, count, what is count? Count is a hash set, hash map, sorry. On this side of the, when you get the key set, you can't write hash set here. You have to write set, because the way that the map classes, the way that the map interface is defined to return a plain set, right? So you don't know the set type that's returned. Once you get the set, you can use it like any other set, though. So I can iterate over the keys, right? I can get the number of times each key appears in the map, and then I can print out how many times that key appears in the map, right? So in this example, I can print out how many times each word appears in the list T. Right? So once you get the key set, you just use it like an ordinary set, right? In other words, you can iterate over the set. You can ask the set, does it contain a particular key, right? If you want to, you can even add something to the key set. So I can add an element to the set, and that actually inserts a new value into the map, which is kind of interesting. Okay, now the values, right? If I can get the keys, can you also get the values? The answer is yes, right? So there's a method called values that returns a collection of the values. Now, we haven't seen this type yet either. So there's another type called collection. That's also in java.util. Right. So collection is also an interface. Right. Now, remember when we talked about lists and maps, lists and sets, right? They had a whole bunch of methods that all looked the same, right? So list has an add method, set has an add method. List has a contains method, set has a contains method, right? The reason lists and sets have those methods in common is because they all promise to implement the collection interface. So the collection interface is, it's the root interface for the collection hierarchy. So it turns out lists and sets, those are all instances of these things called collection, right? Collection's an interface, so it's just a bunch of methods, right? So every list and set implements the methods that are defined in the collection interface, right? Now, what can you do with a collection? Well, I can add something to a collection, right? I can add a bunch of stuff to a collection. I can clear or remove everything from the collection, right? I can ask a collection, does it contain something? I can ask a collection to remove something, right? I can ask a collection for its size. There should be an is empty. Yeah, I can ask a collection if it's empty, right? So that's where all of the methods come from list and set. And that's why you also know that if you have a list or set, they've got these methods in it. It's because the methods are declared in the collection interface. So a collection represents some collection of objects, right? Not necessarily a list. It's not necessarily a set, right? It's just some collection of elements, right? And you can iterate over that collection, right? And so that's what the values method returns. So it returns an instance of a collection, right? You don't know if it's a list. You don't know. It's definitely not a set because the values aren't unique. But you don't know if it's a list or if it's something else. Just know it's a collection. But because it's a collection, you know that you can iterate over the collection. So I can write a little for each loop to loop over the elements of the collection. So in this example here, I'm going to compute the average number of times each string appears in that list, right? Now, the values, that's the count of how many times each string appears, right? So if I want to compute the average of the elements in the values of the map, right? I just compute the average of the elements in vals, right? So at the collection vals, I loop over the collection, right? And I just add the number of times each string appears to this variable num strings, right? The average occurrence is just the sum of all the values divided by the size of the map, right? So here I'm using the keyset size, right? So count.keyset.size. You don't have to do that. You can just write count.size, and it's the same thing, right? So you can get the size of a map using the size method. I don't know why I use count.keyset.size. Anyway, count.size would work just the same, right? So you got the set of keys, right, which you can access using keyset. And then you've got the collection of values, which you can access using the values method. So keyset doesn't specify what kind of set is returned. Okay? So if we go and look at the map interface, which is also in java.util. So when you look at the map interface, this is the interface that tree map and hash map these are the methods that tree map and hash map promise to implement. Right. So when you look at the keyset method here, right, that method says it returns a plain old set. Right, and the values method returns a plain collection. Right. So it doesn't say what type of set or what kind of collection is returned. Right, it just tells you that you have a set or a collection. Right, so both of those methods return a reference to the to an interface. Right, they don't return a reference to a class. Okay, so in the most common form, a Java interface is just a specification of an API. Oops, sorry, you got a crazy cat. Hey, what's going on? Come here. Come on. There you go. Oh, you want out too? All right, out you go. There we go. Okay, sorry about that. All right, so an interface says what methods exist, and it says what they do, but it doesn't say how they're implemented. Right? So the list interface specifies a bunch of methods that every list has to provide. Right? Now, array list has to provide every method that's in the list interface. Similarly, linked list has to provide every method that's in the list interface. Interfaces are types in Java, right? Which is a little bit weird, but that's the way the language works. So classes are user-defined types. Interfaces are specifications of types. Right? They're not implementations. They're just specifications. And that means you can make a variable or a parameter whose type is an interface. Right? If you hit that link there, if you want to read more about this, there's the official Java tutorial. It talks about this. Right? So far when we've been making lists or sets, we've been saying array list t equals new array list, right? But if you want to, you can use the interface name instead for the variable type, right? So I can say t is just a list of string, right? Now, what type of list is it? Well, it's actually an array list of string, right? Or you could write linked list of string on this side. Similarly, for map, right? I can say that count is a map of that maps a string to an integer value. Right? Now, what kind of map is count? Well, it's a hash map. Right? So on the left-hand side, you can use the interface name, and on the right-hand side, you can you specify an actual class. Right? So whatever you put on the right-hand side, that has to be a class. So I can't write list t equals new list, and I can't write map count equals new map. Whatever's on the right-hand side has to be a class. On the left-hand side, you can use the interface name. Now, you might wonder why you'd want to do that. So why don't I just write array list here if I'm making an array list? So the answer is, if I declare t to be a list, right? And say that it's an array list, later on I can change my mind. Right? So if for some reason I decide later on that linked list would actually be a better choice, then I can simply change the right-hand side and write new linked list here. Right? And that means I don't have to change the left-hand side either. Right? Similarly here, if I write map count equals new hash map, and later on I decide, oh, wait, I really wanted a sorted map, all I have to do is change hash map to tree map here. And then I don't have to change anything else. Right? So in other words, I don't have to change hash map on this side to tree map as well. So that's the reason why. So using an interface name gives you the ability to, using an interface for the type gives you the variable, gives you the ability to substitute a different implementation when I want. Okay, so lists, sets, and maps, they are all part of what Java calls the Java collection framework. Well, a function that takes a parameter as an interface. Yeah, so if you have a method and the method has a parameter of type list, you can pass it an array list, you can pass it a linked list, or you can pass it a variable whose type is list. Right? So Java has this ability. Java has this notion of what's called substitutability, right? So I can have a type like list, but I can store a bunch of different types. I can actually store a bunch of different objects in that type, right? I can store an array list in that variable. I can store a linked list in that variable, or I can store some other kind of type that implements the list interface. And that turns out, you'll see in a few weeks that turns out to be very powerful in Java. Right. So yeah, you can write a function that takes in a parameter whose type is an interface, and then you can pass in any object whose class implements that interface. Right. It turns out to be one of the fundamental pillars of object-oriented programming. Okay, so the collection framework is a bunch of interfaces, classes, and methods. That's what makes up the framework. So you've got a bunch of interfaces, and they define what methods the various types of collections support. Right. So you have an interface called set that says what methods all sets must provide. You have an interface called list that says what methods all lists must provide, right? And you have a interface called map that says what methods all maps must provide, right? You then have a bunch of classes, right? And those classes implement the interfaces. So tree map implements the map interface, hash map implements the map interface, and so on and so on. And then you have a bunch of algorithms or methods that operate on the various collections, right? So there's a method called sort in the class collections that will sort a list, right? So you can sort stuff, you can search stuff, and do a bunch of other things with the various collections. So this is the first time you've seen a picture like this. So this picture here is an example of what's called a UML class diagram. So UML is short for Unified Modeling Language. So it's a visual language that lets you describe the structure of an object-oriented program. So this is an example of one type of picture. You'll see, I'm going to show you how to make or how to draw these diagrams when we start to talk about classes, when we start implementing our own classes and our own interfaces and so on and so forth. So this is showing you the organization of the various interfaces in the collection framework. An interface called collection, right? There's an interface called list, and there's your set interface. There's another interface called queue that we haven't talked about yet. If you implemented a queue in your data structures course, that's the interface that we would use to implement. Okay, so what this picture is trying to tell you is that list collection interface. So what that means in Java is that every method that's in the collection interface also in the list interface. Right. And list can add extra methods, right, that are special for lists, right, or that are specific to lists, right? So the list interface adds the method get, right? Sets don't have the get method, but list can add the get method. Right? So list can add extra methods, but it's guaranteed to have everything that's in collection. Is connected to collection via a line and this open arrow. So that means that every method in collection is also in set. Now we have another interface down here called sorted set. Okay, now sorted set has a line and an open arrow pointing to set. So that means sorted set has every method that's in set. It also means it has every method that's in collection. So this the interfaces form what's called a hierarchy, right? So that's the thing that's at the top of the hierarchy. So every interface below it has all the methods that are in here. Sorted set is below set, so that means sorted set has every method that's in set. Sorted set also adds its own methods. Tree set, class that implements the sorted set interface. Right? So a sorted set represents a sorted set. A tree set is a sorted set. So tree set implements the sorted set interface. Sorted set has a bunch of methods that the set interface doesn't have. Because there's things you can do with a sorted set that you can't do with an unsorted set. Right? So for example, I can ask for the first element of a sorted set. Right? I can ask for the last element of a sorted set. I can ask for a range of elements in a sorted set. Right? Those methods aren't provided in the set interface because they don't make sense for something like a hash set. Right? A hash set says its elements can be in any order, so there is no first element, there is no last element. Okay, so everything in red, they include all the methods that are in collection. Everything in blue, or the interface in blue includes all the methods that are in set. Now, map, notice map is not, oh, sorry, I have to stop there. It's 20 after the hour. So anybody have any questions about maps? All right. Anybody have any questions about the assignment? Also not seeing any there. So I'll end the lecture there and finish off talking about the collection framework in the next lecture. I think there's only a few more slides left. No, there's more than a few. So we'll finish. We'll wrap up this lecture at the beginning of the next lecture, and then and then I think we're going to the next lecture. We're gonna start talking about how to make our own classes. So we're moving into part 2 of the notebooks.